Welcome to the Deep Dive. Today we're looking into a really core challenge in AI, how we train these massive large language models, or LLMs. They're just getting bigger and bigger, and training them well and efficiently is a huge hurdle. Standard ways are hitting walls. So our mission today is to unpack a specific technique from a paper called Taming LLMs by Scaling Learning Rates with Gradient Grouping. It's proposing a new way to optimize these giants.
And just to set the scene a bit, the difficulty really comes down to the sheer scale and also the complex ways these LLMs learn internally. We're talking billions, maybe trillions of parameters. We have tools, adaptive optimizers that adjust learning speeds for each parameter, but, well, they weren't really built for this kind of scale.
Sure.
They come with some serious downsides.
Right, so these adaptive optimizers like AdamW, that one's really common. They're clever because they look at the history for each parameter, how its gradient is changing, and try to find the perfect learning rate. But you're saying at LLM scale, they run into trouble.
They do. The paper points out a few key issues. First off, memory. To track the history and adapt the rate for every single parameter, they need to store stats like momentum, variance estimates. You do that for billions of parameters, and the memory footprint is just substantial.
And memory is often the bottleneck when you're training these enormous models.
It really is. And beyond memory, these standard optimizers can sometimes make the training unstable, or they might converge quite slowly. You don't always get the best result quickly. And then there's this issue with parameter-efficient fine-tuning PEFT methods.
PEFT, like Loray and techniques like that, where you only train a small part of the model to save memory and compute.
That's the one. You'd think optimizing fewer parameters would be easier.
Yeah, it seems logical.
But the source notes that while PEFT helps with efficiency, it often doesn't perform quite as well as training the whole model from scratch. Table 4 in the paper actually shows this gap pretty clearly. And other compression methods, they can be a bit hit or miss, kind of inconsistent, as you see in Table 5. It often feels like this trade-off, efficiency versus top performance.
Okay, so the challenge is clear. Standard optimizers are memory-heavy, can be unstable, and even with efficiency tricks like PEFT, you might lose performance. So this paper proposes SGG, scaling with gradient grouping, to tackle this. What's the basic idea?
The core concept is quite neat, actually. SGG isn't a whole new optimizer. It's designed as an optimizer wrapper.
A wrapper, so like an add-on.
Kind of. Think of it as an enhancement layer that you put on top of your existing optimizer, whether that's AdamW, SGD, whatever you're using. Its main job is to improve how that base optimizer estimates and uses the learning rates for each parameter.
Like an intelligent assistant for the optimizer.
You could put it that way. The central idea, which Figure 1 helps visualize, is that it dynamically groups related gradient statistics within each layer. Specifically, the paper focuses on grouping the momentum vectors.
Momentum vectors. Remind me what those are again?
Sure. So instead of just using the raw gradient direction at each step, many optimizers use momentum. It's like a running average of past gradient directions smoothed out. It helps the optimizer build speed in consistent directions and avoid getting stuck in little oscillations. SGG looks at these momentum vectors within a layer and groups them together. Then, once it has these groups or clusters, it applies a cluster-specific scaling factor to the learning rates of the parameters within that cluster.
So it's looking at how groups of parameters are moving together based on their momentum and tweaking their learning speed based on that shared behavior.
That's the core idea. But crucially, it's not about setting one single learning rate for the whole group. That would throw away important information about individual parameters. Instead, SGG scales the existing per-parameter rates that the base optimizer already calculated. It multiplies them by this group-based factor. So you get the benefit of the group constraint while keeping the fine-grained individual adaptation.
Okay. Scaling, not replacing. That's a key difference. But why does grouping momentum actually help? What did their initial studies show? They looked at Llama 1B on the C4 dataset, right?
They did, and Figure 2 is quite insightful here. It showed that if you look at the momentum vectors in a layer, they aren't just random. There are clear clustering patterns. Parameters within a layer seem to have some shared structure in how their updates are behaving. They're not all moving totally independently.
So there's some hidden structure in the learning process that standard optimizers might miss.
That seems to be the case. And SGG tries to leverage that structure. The studies also found two other critical things about these clusters. First, the patterns change depending on what statistic you look at. Raw gradients might cluster differently than momentum, which might cluster differently than the final learning rates. This means the grouping needs to be dynamic. You can't just predefine fixed groups. The groups have to adapt as training goes on.
Makes sense. Training dynamics aren't static.
And second, and this really supports SGG's approach, they found significant variation within each cluster when looking at the individual parameter learning rates. If you just average the rate for the whole cluster, you'd lose important details about how each specific parameter should be updated. So this supports their decision to scale the existing rates, not just replace them. You preserve the individual signal, but guide it with the group context.
Okay, so the studies show momentum clusters exist, they're dynamic, and scaling preserves important individual info. How does SGG actually do this in practice? Algorithm 1 lays it out, I believe.
Right. It fits quite smoothly into the optimization loop. After your base optimizer calculates the momentum vector, let's call it NTL, for layer L SGG comes into play. First step, dynamic grouping. Within each layer, it clusters these momentum vectors into a set number of groups, say K groups. The paper tested a few methods, as shown in Figure 3, and found mini-batch K-means was a good trade-off between cluster quality and speed. So that's the default. This clustering doesn't happen every single step, though. That'd be too slow. It happens periodically, maybe every T iterations. Figure 6a suggests setting T to around 5% of total training steps worked well empirically.
Okay, periodically recluster the momentum in each layer. Got it. What next?
Next is cluster-specific scaling. Here, SGG calculates a scaling factor, STLC, for each cluster C it just found in layer L. They use a metric they developed called the median of deviation to average, or MDA.
MDA. What's that measuring?
Think of it as measuring the consistency or stability of the momentum vectors within a cluster. For each cluster, it calculates its MDA, DTLC. This basically looks at how much individual momentum vectors in the cluster deviate from the layer's average momentum. A low MDA means the vectors in that cluster are behaving quite similarly, quite consistently relative to the layer average. They also compute a global MDA DT across the whole model as a reference point. Table 2 indicates MDA worked well for this.
Okay, so MDA measures cluster consistency. How does that become a scaling factor?
The scaling factor for a cluster C, STLC, is calculated as the global MDA, DT, divided by that cluster's MDA, DTLC, plus a tiny value to keep things stable. You can see the formula in equation 6. What this means is clusters with more consistent momentum, lower DTLC, get a larger scaling factor. Clusters that are more spread out or varied get a smaller factor. It sort of encourages more progress in the stable, predictable parts of the model, while being a bit more conservative where things are more varied. These factors are also smoothed over time using an EMA, an exponential moving average, as per equation 7, which is pretty standard.
And this smoothed cluster-specific scaling factor just gets multiplied by the learning rate the base optimizer already figured out for each parameter.
That's right. The adaptive learning rate of L for a parameter in layer L is simply multiplied by the scaling factor, SANTI LCTL, for the cluster that parameter belongs to. That's how the group information influences the individual update. The paper also mentions some practical points. Because it's a wrapper, it works with different optimizers, SGD, AdamW, Apollo, without changing the model or pipeline. And to save precious GPU memory, things like which cluster each parameter belongs to can be stored on the CPU. Tables 1 and 3 show this has minimal overhead. They also give some default settings like K3 clusters, reclustering every T500 steps, and an EMA beta of 0.99, which seem pretty robust in their tests, based on Table 9 and Figure 6.
That makes the mechanism much clearer. Group momentum, measure consistency with MEA, use that to scale the individual rates. So how did this actually perform in their experiments? Did it deliver on the promise?
The results look quite strong, yeah. They tested it across different scenarios using standard metrics like perplexity for language modeling and accuracy for classification. First, for LLM pre-training on that C4 dataset, with llama models from 60 million up to 1 billion parameters. SGG consistently led to faster convergence, meaning it learned quicker and lower validation perplexity compared to baselines like standard AdamW, CAME, or Apollo. You can see this in Table 4 and Figure 4. For instance, Adam plus SGG achieved lower perplexity than just Adam alone.
Okay, better pre-training. What about that PEFT challenge, using LoRa for pre-training?
That's maybe one of the standout results. The paper reports that combining LoRa with SGG, LoRa plus SGG, allowed low-rank pre-training performance to get very close to full-rank training performance across different model sizes. This is apparently the first time they saw this. For their 1 billion parameter Llama model, LoRa plus SGG hit a perplexity of 14.73, which is really close to the 14.30 achieved by full-rank AdamW. And importantly, it was big improvement over just using LoRa by itself, about 4.5% better PPL for the 1B model, and over 10% better for the 130M model, according to Table 4.
Wow, so SGG might really bridge that gap between PEFT efficiency and full-rank quality, at least in pre-training. That feels significant.
It does seem that way. And the benefits carried over to LLM fine-tuning, too. On the GLUE benchmark that supervised fine-tuning on tasks like text classification with Roberta, adding SGG to AdamW gave average accuracy gains of about 1.0% for full-rank tuning and 1.27% when using LoRa with rank 4. Table 5 shows the details across different tasks. Then, for common-sense reasoning tasks, fine-tuning Llama 7B with LoRa, adding SGG improved the average accuracy by 2.9% across 8 tasks compared to just LoRa. On one task, OBQA, the gain was over 4%, Table 6. And even for direct preference optimization, or DPO, which is used to align models better with human preferences, they fine-tuned a Quinn model using LoRa. AdamW plus SGG got the best LoRa accuracy at 72.02%. That was 1.8% better than baseline AdamW with LoRa, and interestingly, slightly better than full-rank AdamW, Table 7.
Works for standard fine-tuning PEFT, even alignment like DPO. Do they try multimodal models?
They did. SGG showed benefits for multimodal language models, MLLMs, too, using Elevate variants. It boosted AdamW's average accuracy by 1.0% and Adafactors by 0.6% on multimodal benchmarks. Table 8. There was a nice 2.4% gain on the VizWiz task with Adafactor plus SGG. It also helped when using QLoRa, which is 8-bit fine-tuning, improving accuracy by 0.6% on average.
Okay, so it seems consistently helpful across pre-training, fine-tuning, different tasks, different models, even multimodal ones. The paper also mentioned robustness, didn't it? How sensitive is SGG to things like learning rate or batch size?
That was another key point they highlighted. SGG seemed remarkably robust, especially when you start changing the learning rate or batch size significantly. Figure 5 illustrates this well. They fine-tuned a Quinn model, and when using standard Adam, the training could become unstable. The loss might shoot up if they use very large batch sizes or push the learning rate too high or low. But with Adam plus SGG, the validation loss remains stable across a much wider range of batch sizes, from 128 all the way up to 4096, and also across a broad sweep of learning rates, from 1E5 up to 0.1.
So it makes the whole training process less fiddly, less sensitive to getting those hyperparameters exactly right.
It appears so. The paper suggests this might be because SGG helps manage gradient outliers parameters or groups moving erratically and dynamically adjusts rates based on the stable group dynamics. This seems to lead to more reliable training, even when you push the settings into territory where standard optimizers might falter.
Right, so we have performance gains, faster convergence, better PEFT results, multimodal effectiveness, and this added robustness. It covers a lot of bases. Did the paper mention any limitations or where research should go next?
Yeah, they pointed out a few areas. One is to maybe explore different ways to do the grouping itself beyond the online k-means they used. Maybe other clustering methods could be more effective or faster. Improving the computational efficiency is another area. That clustering step, while periodic, still adds some overhead, especially for really huge models. Finding ways to make that faster would be good. And finally, just broadening the evaluation. Testing SGG on different kinds of data, maybe very different model architectures, or even larger scales than the 1 billion parameter models they tested, to really confirm how widely it applies.
Good points for future work.
Yeah.
So to wrap up, what's the core value proposition of SGG here?
I'd say SGG presents itself as a practical, flexible way to enhance LLM optimization. It's a wrapper that seems to consistently deliver better performance, faster training, and more robustness across a whole range of models and tasks, including MLLMs. And a big plus is that it integrates easily with the tools people are already using, like AdamW and LoRa. And perhaps a final thought to leave you with, drawing from the paper's perspective. SGG demonstrates the potential of using group-level dynamics to scale adaptive learning rates. It's one specific approach, but the underlying idea, leveraging collective behavior to refine individual updates, seems really powerful. Future work could explore many other ways to define groups, measure their dynamics, and apply those insights. It feels like there's still a lot of room to improve how we train these increasingly complex models.
That idea of optimizing by looking at both the individual parameters and their collective movement, that's definitely something to chew on. It really makes you wonder what the next breakthroughs in training efficiency will look like.